Mechanisms. Mechanisms. Last class we talked about mechanisms. We learned how to figure out the reaction rate, the rate law from the mechanism. All right, there's one thing I wanted to finish up about mechanisms that I just didn't quite get to last class, okay? And that is molecularity. There's a lot of information in this in your guided notes and in the textbook, okay? Like I said, there was just like this one last problem I didn't quite get to. So molecularity, let me back up. In order for reactions to occur, two things must happen. Well, in order for reactions to occur, particles have to be colliding. Those reactant molecules have to be colliding. And two things have to be true about those collisions. There has to be enough energy for those collisions to result in a reaction, and the collisions have to occur in a favorable orientation. Okay, so think back to like biology. You've heard about like enzymes and substrates, like lock and key type thing, and how enzymes unlock the substrate and it causes the reaction to occur. So kind of like that, but in chemistry, we're dealing with much smaller substances. You know, we're dealing with, for example, an H2 molecule, which is really, really, really tiny, whereas in biology, those substrates are these big, large proteins where their shapes can change over time, okay? Or you can change their shape using an enzyme. So molecularity is looking at how many molecules of reactants, how many moles of reactant are actually colliding together. Okay? So in the first step, how many molecules are reacting together? 2. We have 2 NO molecules that have to collide. What about in the second step? How many molecules are reacting together? 2 as well. We have to have one N2O2 and one H2. And then what about in the third step? 2 as well. So every single one of these steps is called bimolecular. It's just how this mechanism ended up being, that all 3 of them were the same. If one of them had only one particle, it'd be called unimolecular. If there were 3, it'd be trimolecular, or sorry, not tri, it'd be termolecular, and then 4 would be quadmolecular. Okay? But you just look at however many reactant particles there are, and, you know, uni, bi, ter, quad, so on and so forth, okay? Now, from this, we're going to do a few things, and we're going to actually add a question to this. Let's first add up all of the steps to show that it equals the overall reaction. Now, if this were an actual test question, I wouldn't give you the overall equation. I would just give you the individual steps and be like, all right, what's the overall equation? So let's ignore that we know the overall equation for now. Let's just look at the 3 steps of the mechanism, add them up, canceling out things that cancel out. Right? So, do we have substances that are the exact same on both sides? N2O2, here and here, so that's going to cancel out. Anything else? N2O, here and here, so that cancels out. Does anything else cancel out? Nope, because there's nothing else that's on both sides. We have things that are, like for example, the H2s, they're both on the reactant side, but we don't have anything on the product side that will cancel with that. So we're just going to bring everything down. So we're going to have 2NO plus 2H2, because those add together, goes to N2 plus 2H2O, because those add together. Now the things that canceled out, what do we call those? The N2O2 and the N2O. Intermediates. I'll review those terms in just a moment. Let me just finish writing this. Okay. Remember, intermediates are substances that are produced early on and then get used up later. So if it's a product in an early step and then a reactant in a later step, it's an intermediate. Notice how our 2 intermediates are not part of the overall equation. Intermediates and catalysts will never be part of the overall equation because they are things that are going to cancel out. You're going to find them on both sides of the arrow. Catalysts are the ones that are reactants first and then get produced later. Like you use them early on and then we get them back out at the end or towards the end. Okay? But if you cancel it out, it's a catalyst or an intermediate. And make sure you know the difference between the two. These are great like multiple choice type questions. Okay? So we're going to add one question to this. Let me just finish writing it. If the rate law was determined to be rate equals K All right, so last class when we were doing mechanisms, we were figuring out the rate law from the slow step, which is also called the rate determining step. But with this problem, we don't know what the slow step is. So you can, if given a rate law, you can figure out which one had to have been the slow step. So it's like working backwards. Okay? So if the rate law was determined to be rate equals K N2O to the first, H2 to the first, which step had to be slow? What do you think? Why the third one? Exactly. So we know that from the rate law, we have to have a step which has N2O and H2 as reactants, and we have to have coefficients of 1 in front of both of those. The only one that that applies to is the third step. I know it kind of crossed through some things, but remember this was N2O. So therefore the answer is the third step, or step 3. Okay? So make sure you can answer all types of questions relating to mechanisms. Sometimes you have to give me the rate law. Sometimes you need to figure out what the slow step is. Okay? Cool? All right, number 15. So, when a certain substance's concentration is doubled, the rate gets multiplied by 8. It proceeds 8 times as fast. So we can figure out what the order is with respect to that substance. Okay? This is also a great multiple choice type question. Okay? So what letter do we want to give for this substance? A? Okay. So we're going to say this is substance A. We're doubling the rate, we're doubling the concentration of the substance. Right? So, and then the rate proceeds 8 times as fast. So you can actually set up a little, kind of like a method of initial rates problem, where when, just pick 2 numbers as long as one of them is double the other. So, okay, so let me back up. So rate equals rate constant K times whatever substance this is to the X. Okay, and X is the order. We're solving for X. We know that the rate is going to proceed 8 times as fast if we double the concentration of A. So let's kind of set up a little problem that looks like this. Eight over 1 is 8 times 1? Yes. It doesn't matter what 2 numbers you picked here as long as the top one was 8 times the bottom one, because this is the rate. K is our rate constant. 2 is the concentration of A when we've doubled the concentration and we started off at 1. Again, it doesn't matter what 2 numbers you picked here and here, as long as the top one was double the bottom one. We could have done 500 and 250. We could have done 1,000 and 500. It doesn't matter as long as the top one is double that of the bottom one for the concentration. And the rates, the top one needed to be 8 times that of the bottom one. We could have done 32 and 4. Like, it doesn't matter. Okay? So now, what's going to cancel out? Well, K is going to cancel out. And really, this is going to reduce down to 8 equals 2 to the X. So what's X? 3. 3. So therefore, it's third order for that substance. Had the rate only doubled, like it proceeded 8 times as fast, say the rate doubled while the concentration doubled, then it would be first order. If the rate quadrupled when the concentration was doubled, then it would be second order. Knowing how to figure out those exponents is really beneficial. And being able to do it without a calculator, things like this, is really beneficial. Great multiple choice type questions. I said this before, this class is not a calculus-based course. A lot of the formulas that we use are derived using calculus, and if you go on to take upper level chemistry courses in college, you'll need some calculus for it. But AP Chemistry, first year chemistry, is not calculus-based. It's algebra-based. So really, honestly, if you're in a higher level math, you might need to brush up on some of your algebra skills. Because I don't want you to make careless errors in rearranging a formula just because you might be able to integrate something, but then you can't remember how to solve for x. Okay? So make sure you brush up on those skills. All right. I'm going to do a little mini lecture. If you want to write any of this stuff down, I suggest you do it on the back on page 10. Page 10 does not need all that space for number 17. That was just poor planning on my end. But now you get some extra space. So I'd maybe like cut this in half and use the bottom half to write any of this next stuff down. Okay. For the factors that affect reaction rates lab, you should have learned there are 4 ways to increase reaction rate. Okay, or rate of reaction. So one of the ways is to increase the temperature. Another way is to increase the surface area of the reactants. Third way is to increase the concentration of the reactants. And the fourth way is to add a catalyst. Okay, those are those 4 ways to increase the rate of reaction. And remember, for reactions to occur, we have to have collisions that have enough energy and in the proper orientation to make those reactant molecules become products. All of these ways to increase reaction rate will affect those collisions. Okay? The reason adding a catalyst increases reaction rate is because it lowers the activation energy. Adding a catalyst provides more favorable orientation of those molecules. That's like adding an enzyme to a substrate. It changes the shape of it and allows the reaction to occur faster. Okay? So, activation energy, that'll be time. I'll make it an endothermic reaction. So these are my reactants, these are my products. This right here, that's my activation energy. Okay? All reactions have this reaction pathway. Some of them are exothermic, some of them are endothermic. But all reactions need to reach that activation energy in order for them to occur. That activation energy is going to be constant, or it's going to be the same at no matter what temperature or how much of that substance you have. All of them need to reach that activation energy. Okay? When you increase temperature, the reason the reaction goes faster is because those particles reach that activation energy faster because they have higher kinetic energy. The reason why if you increase surface area of reactants, they reach that activation energy faster because there's more sites of those particles exposed, leading to more collisions. More collisions, you reach the activation energy faster. If you increase the concentration, you literally have more of those substances there, therefore more collisions. Adding a catalyst actually lowers the activation energy. Okay? That's the only one that does. So the pathway for adding a catalyst might look like this. The starting and ending is still the same, but now we have a lower activation energy. Okay? So that would be the pathway with a catalyst. Okay? Now, we're mainly going to talk about temperature for right now. We have actually a formula that we can use called the Arrhenius equation. You do not need to memorize it. Okay? But it looks like this. Okay, I don't want you to memorize this. It's not on the formula sheet either, but I don't want you to memorize it. Okay? Normally when it's not on the formula sheet and I think you're going to need it for the AP exam, I'm like, memorize it. This one, you're not going to need it for the AP exam. This is one of the few places where I go beyond what the AP exam will be testing you on. Because I feel that it's important to understand the math behind it, and it helps you understand the conceptual part of it as well. Okay? But I'll give you this formula on the test. All right, so what's K2 and K1? Can you be more specific? What type of constant? Rate constant. That's a rate constant. Now, when we were doing method of initial rates, all of those experiments, when we're changing the concentrations of our reactants, they're all occurring at the same temperature. Because rate constant is temperature dependent. As soon as you change the temperature, you're changing the rate constant. They're directly proportional. The higher the temperature, the higher the rate constant. And that's why mathematically, increasing the temperature increases reaction rate, because your rate constant is higher. Your concentrations of your substances are the same, but in that rate law, the only thing that's changing is the rate constant when you change temperature. Okay? EA is our activation energy. R is a constant that's on your formula sheet. There's actually 3 R values on your formula sheet. 2 of them have to do with gas laws. Third one, we're actually going to use it in many, many, many units, and that is the one that has energy, or joules in it, and that's 8.31 joules per Kelvin mole. Okay. So looking at the units of R, what units do you think our temperature needs to be in? Kelvin. Need to have temperature in Kelvin. So we're going to be looking at the same reaction done at 2 different temperatures and looking at their rate constants to use that with activation energy. Okay? But like I said, the reason mathematically that increasing temperature increases the rate is because you're actually increasing that rate constant. Conceptually, what's happening is more of those particles have greater kinetic energy, so more of them are going to reach that activation energy at a faster rate. Conceptually, that's what's happening. Mathematically, it's because that rate constant is increasing. Okay? So now we're going to do a couple problems, and then we're going to do a problem from your homework, and then I'm going to let you work on your pre-lab questions, which are all using this type of stuff. Okay? All right. So we have this reaction. This is an organic reaction. It's a conversion of cyclopropane to propene. So this reaction was done at 300 degrees Celsius, and we measured the rate constant to be 2.41 times 10 to the negative 10 seconds to the negative 1. And then it was done again at 400 Celsius, and we found the rate constant to be this. And we're going to calculate the activation energy. Let me rewrite the formula. Now remember, you don't need to memorize this. I'm going to give it to you for your tests and stuff like that. But I'm going to show you how to use it. Okay? So, first off, what do we need to do? I wouldn't rearrange the formula to solve for EA. I would just plug everything in that I know and solve for EA that way. That's how I'm going to do it. But before I plug in, what do I need to convert? I need to convert my temperature to Kelvin. Okay? Yes. Put it in Kelvin. Just always get in the habit of putting things in Kelvin when you need them in Kelvin. So what is 300 Celsius in Kelvin? 573. I don't care about the 0.15. And what is 400 Celsius in Kelvin? All right. So now we're going to plug in. Now, make sure you keep, because notice it's natural log of K2 over K1, but then it's 1 minus T1, or sorry, 1 over T1 minus 1 over T2. So it gets flipped. So make sure you keep, like, 2.41 times 10 to the negative 10 is with 573, and then 673 is with this other one. So make sure you keep things straight, okay? So natural log K2 is the 1.16 times 10 to the negative 6 seconds to the negative 1. K1 is 2.41 times 10 to the negative 10. Notice that the higher temperature has the higher rate constant. 1.16 times 10 to the negative 6 is a much larger value than 2.41 times 10 to the negative 10. Higher the temperature, the higher the rate constant. Equals, EA is what I'm solving for. What is R? Okay. And then 1 over T1, which is 573, minus 1 over 673. I want to say that if you're solving for temperature, you have to have it in Kelvin. Like the next problem, we're going to be solving for a temperature, and I think there you need to have it in Kelvin, otherwise it won't work out. Yeah, technically here, if you didn't convert it to Kelvin, it wouldn't have made a difference because the change would be the same, but I think when you're solving for temperature, you need to have it in Kelvin. In the next one, we're gonna solve for T2 and then calculate the change, but I guess it really depends on what the problem's asking you. Okay. All right. Now, when I did this, I solved the entire left side first. I did the natural log, and I just kept everything in my calculator because then I can use those values. So I did, natural log of 1.16 e negative 6 divided by 2.41 e negative 10, and I get 8.479. But I'm leaving that in my calculator because there's obviously a lot more numbers. I leave that in my calculator so I don't truncate it too early. Equals EA over 8.31, and then I solve the subtraction. And I get 2.59 times 10 to the negative 4. And again, I truncated that, but I leave it in my calculator so I can then reuse it. So solving for EA, what I did, now how you might be able to do this all in one step because you understand the algebra. I like to do it a couple steps. Now I took the left side and I divided it by the 2.59 times 10 to the negative 4, and then I multiplied it by 8.31. And you should get a very large number. And I rounded it to 3 sig figs. So 272,000 is our activation energy. What's our unit? Joules per mole. Because only the Kelvin canceled out from our R value, and obviously the seconds to the negative 1 canceled out as well. So, or you could have said 272 kilojoules per mole. Either one. If it doesn't ask for it in a specific unit, give it in whatever unit you end up solving it. Don't make a careless error, because that actually already happened, where a student gave it to me in joules and then also gave it to me in kilojoules, but did the conversion wrong. And I had to take off points, because I have to grade what you give me. If you're telling me that 272,000 joules per mole is the same as 27.2 kilojoules per mole, you're wrong, because it's really 272 kilojoules per mole. Okay? So unless it asks for a specific unit, just leave it in whatever unit you find it in. Don't waste the time going that extra step. Okay? And also risk making a careless error like that. All right? So now with the next one, we are given the activation energy and we're going to find a temperature. Okay? Let me write down the formula. Now you should still be able to conceptually tell me that, you know, rate constant is increasing when temperature increases and stuff like that, but doing actual calculations with it, I will not hold you responsible for that without giving you the formula. Okay? All right, so what do we know for this problem? Okay, so we're told that the activation energy for that decomposition is 1.0 times 10 to the second kilojoules per mole, and we want to know what is the temperature change necessary to double the rate at room temperature. Now, for chemistry, room temperature is 25 degrees Celsius. Okay, 25 degrees Celsius. So that's my T1. So what is T1 in proper units? 298. So T1 is 298 Kelvin. T2 is what we're solving for. It's going to be whatever, and then we'll subtract to find the difference. Okay? Or I guess you could solve for 1 over T1 minus 1 over T2, and then, you know, rearrange that to find the difference. I find it easier just to solve for T2 and then subtract. All right. So we know that the rate has to double in order for this to occur. I didn't give you K2 and K1 though. But what do we know about K2 and K1? K2 has to be double that of K1. Because when we're changing the temperature, are we changing concentration? No. All we're changing is the rate constant. That's what's causing the rate itself to double. It's because the rate constant is doubling. Okay? So we know that K2, I want that to be a lowercase k. K2 has to be double K1. So it doesn't matter what two numbers you use as long as when you divide them, you get a 2. Or you could just say, hey, natural log of 2 equals, and then plug in everything else you have. Now, what's R? That's joules per Kelvin mole. But wait, my activation energy was in kilojoules per mole. They don't match, so I need to convert one. Does it matter which one I convert? Nope, it doesn't matter if you convert the kilojoules to joules or the joules to kilojoules. It doesn't matter as long as you make them both match. Okay? Which one do you want to convert? Okay, so if we convert the activation energy, 1.0 times 10 to the second kilojoules per mole is 1.0 times 10 to the what? Fifth joules per mole. Okay, over 8.31 joules per Kelvin mole. I'm going to erase this R value because I'm going to run out of room. I did not space this out well. Times 1 over T1, which is 298, minus 1 over T2. And now we're going to solve for T2. So natural log of 2 is 0.693. There's obviously more that you can have in your calculator right now, but for right now I'm just going to write down that. And then I'm going to do 1.0 to the fifth divided by 8.31. And again, I truncated that, but that's okay because I'm leaving it in my calculator. And now I'm going to take that 0.693 and divide it by the 12033, blah, 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 blah. And now you just need to solve for x. And like I said, this is where you might need to brush up on some of those algebra skills that you may not have used in a few years, depending upon what math you're in. Through a few more steps, which I'm not going to go through because I feel like you need to, like, you should definitely practice solving for this, but you should eventually get that x is 303. And I'm ignoring sig figs because I don't want to deal with them for this. And that's Kelvin. So what is my change in temperature? You wouldn't put a degree sign in front of Kelvin. Hey, guys. You wouldn't put a, no, you don't put a degree sign in front of Kelvin. So you can either say 5 Kelvin or 5 degrees Celsius. They're the same thing. Because it's the same scale, it's just shifted. So in order to double this reaction rate, for whatever reaction this is, in order to double it, you have to increase the temperature by 5 degrees. It's not a huge temperature change to double the rate of reaction. Yep, it doesn't matter. Because in order to convert, if we converted both of our kelvins back to Celsius, we would still get a 5-degree difference. Fahrenheit wouldn't be a 5-degree difference because it's a different scale. But yeah, Celsius and Kelvin, it's the same scale. It's just, it's either starting at 0 or starting at negative 273. Like, okay? We're going to do one more problem. And this is homework 4B number 2. I'll pause for a moment while I grab something. So this problem is like your lab. This is like the Crystal Violet lab. You will see this in both the pre-lab and the post-lab. Okay? So do you think it's important that you know how to do this? Yeah, because you will have seen it in the homework, and you will have seen it in the pre-lab, and then you'll have seen it in the post-lab. So hopefully you'll know it by the test, right? Okay. So, most of the time, when we were doing integrated rate law, figuring out the rate of reaction from graphical analysis, we were looking at decomposition reactions. How many reactants does a decomposition reaction have? 1. So most of the time, we're looking at a single reactant reaction and looking at how its concentration is changing over time. You can also do a graphical analysis to figure out the order of reaction with respect to one of your reactants when you have 2 reactants in a reaction. But you have to manipulate your concentrations so that only one of them is going to change over time relatively. So the way to do this is to take a reaction, for example, oxygen atoms plus NO2, okay? And keep one of them in a huge, huge, huge excess. In this case, NO2 is in such a large excess that yes, its amount is going to change over time, but relative to what it's starting with, it's barely anything. And then the other reactant, for example, oxygen atoms, is going to change more over time compared to what it starts with. That's in a much smaller initial quantity. You're going to do this exact same thing in your lab. You're going to be reacting this crystal violet compound with hydroxide ions. And hydroxide ions are going to be in the large excess, so when you're looking at the rate of reaction, you're looking at how the crystal violet is changing over time. This is called pseudo rate constants or pseudo rate laws. Okay? So, we're going to run through, just like we did with all of our other graphical analysis, where we're going to take our time and our concentration, plug that in, L1, L2, and then figure out L3 and L4. One thing I want to point out is this unit for concentration is a little bit weird. It's something you might not have ever seen before, and that is atoms per centimeter cubed, or molecules per centimeter cubed. It's just another type of unit for concentration. Because concentration, you're used to seeing moles per liter, right? So it's moles of particles per volume. Molecules per volume. It's just another way to see unit concentration. Okay, that's it. It's just a weird one, but it's concentration. Okay, so we're going to pull out our calculators. We're going to turn them on. We're going to go to our list. We're going to clear them out so that we can fill them in. Okay, I'd already loaded these in. So L1, make that your time. L2, make that your concentration. And then what do we make L3? ln of L2, right? I scroll up to L3 and I type ln of L2, enter. What do we make L4? 1 over L2, exactly. Okay, so get your lists all made. And then I don't have a lot of room on my board to write down all of the R squared and A values, but you can write that off down in like the margin of your paper. But once we get all those in, then we're going to run the linear regression. I went through this last class and I recorded it, so if you need a refresher on that, you can go watch it. Okay, on how to do all of the linear regression things. Okay? But get all your lists propagated and figure out the order, and we'll check back in once you do that. Okay, so I'm going to pause this while you figure that out. All right, so you should have figured out that it was first order. Up on my calculator right now, I have the linear regression for L1, L3. That's if it were first order. Remember, L1, L2 is 0. L1, L4 is second. So L1, L3 is first order. That one gave me the R squared value closest to 1. If this were a test question, I wouldn't need to see all of the individual regressions. What I would need is, there's really no way for me to test your calculator. But if I give you a set of data, if it's what was the order of this reaction with respect to something, you need to say, first order with respect to oxygen atoms, because the R squared value for natural log of oxygen atoms versus time was closest to 1. Okay, that's enough justification for that. Okay, if I gave you 3 graphs, it would be the one with the straightest line. Okay, so that one's closest to 1. Now, what's the rate law from our linear regression? We got that it was first order, right? So rate equals K times the concentration of oxygen atoms to the first. Yeah? But that's only for oxygen. We have another reactant, and that's nitrogen dioxide. So this K value, we're going to call that K prime, because that is a pseudo rate constant. Okay? It's not the overall rate constant, because we have to take into consideration the nitrogen dioxide as well. And then the K prime value is here in our calculator, And that is our slope, the absolute value of our slope. Okay? So our K prime value is 100 point. What's the unit for that K prime? That K prime is only for first order. So remember, when it's first order, we just look at the time and do 1 over time. So seconds to the negative 1. No, it's absolute value of the slope. I also got negative 100 as my slope. K is absolute value of A. Mm-hmm. All right, absolute value of slope. K is always absolute value of slope. All right, so now B is what we're going to do to figure out the overall rate constant. So we're told that it's first order with respect to NO2. So let's write that rate law. Rate equals regular K times, we already figured out that oxygen was to the first, and now we're told that NO2 is to the first. So now we have two reactions, or we have two formulas. Rate equals K prime times oxygen atoms to the first, and rate equals K times NO2 to the first times oxygen to the first. So therefore, K prime is this. This is K prime. So if we know, sorry, not that. Let me rearrange this. I'm going to write this the other way. I'm going to put NO2 down first and then oxygen. It means the same thing. Okay, so K prime is this. Okay? Because if it's the same rate, I'm hearing, oh, yay, I get it. Okay? So that's K prime. So K prime equals K times NO2 to the first. Let's fill in what we know. What's K prime? 100, and that's seconds to the negative 1 because we care about units. K is what we're solving for. What's NO2? That was that initial concentration, which was in such large excess that its amount really didn't change over time. So 1.0 times 10 to the 13th molecules per centimeter cubed. Or molarity if, this was a different type of problem. Remember, that's just concentration. So now we divide to find the actual rate constant. Because it's like the rate constant from the linear regression is including NO2's concentration. Okay? So now we divide that out to get rid of NO2's concentration, just have the real rate constant, which is what? (1.0) times 10 to the negative 11. And what are my units now? Centimeters cubed over seconds times molecules. Cool? All right. So that is pseudo rate constant. And that is just like your pre-lab, just like your post-lab, so make sure you know how to do this.